1, 2, 3, 4, 5, 6, 7, 8. So if you add all of them divided by 8, you would have gotten an average value of 7, isn't it? Which is good. And if you look at this course, you can see how if you have a mean of 7, and you can see the values are between 7, 6, and 8. Then if you have the average value to be 7, then it's good, isn't it? Then let's look at this one also. You see 12, you see 2, you see 0, you see 14, you see 10, you see 9, you see 5, you see 4. This is what? The set of values. The average value by summing and dividing it by 8 of them will give us what? Another average value of 7. Now, from this question, I'll ask another one again, that which of these two, you see that the mean value is the same thing, right? Irrespective of the numbers that are inside these sets. Which of them provide us with a better description of the value than the other? Who is helping us? Simon, do you want to help us? Which of them, the first one or the second one, which of them give us a better description of the data?
Sir, let me try. Hello, sir.
Simon.
Sir, to me, there is the first one.
Simon, can I?
Hello, sir.
Why is it the first one? Because I told you it's not just about selecting the first one. The why is what I'm interested in much.
Sir, let me try.
Let's give him the chance to do so before. Simon, tell us why.
Yes. My reason is that if you look at the first values, we have 786, 77687. And if you compare this, the first one to the second one, the first one has lesser values than the second one, and that is my reason.
Lesser values.
Yes.
Okay. That is your reason. Let me call somebody also here. Chumesi. Chumesi, I've not heard your voice before. Chumesi, are you with us?
Sir.
Chumesi.
No, not Chumesi, sorry.
I've mentioned Chumesi.
Yes, sorry.
Chumesi is not with us. So it's equals to he's not in class. Mark.
I'll pick the first one because the values are closer to the mean.
Hello. Okay, that is your reason,
the
right?
Values, the values are closer to the mean. The second one, the value is greater from 0 to 7. Then from 7 to 14, there are about 6 intervals. So I'll pick the first one, which is closer to the values.
Okay. Now, whilst picking this, one question you could have asked yourself is that if there are 8 observations throughout, right? 18.
Yes, sir.
All of them. If you ask yourself that these are 8 people in a class, you don't know the average age of them, right?
Okay. Yes,
so you want to close your eye and or after computing their average age, you want to say that, okay, in fact, if you go to this class, if you randomly pick anybody at all, the person would have been 7 years old.
or closer.
That is the average.
Okay.
That is what it's supposed to be telling us. Then you ask yourself, okay, of these two examples, which one would give me a much better idea that if I come to this class and I pick 7, will the 7 reflect, okay, there are 8 people in that class. The smallest person or the youngest person is 6 years and the oldest person is 8. So if I come around or I come to that class and I pick at random and the person is 7 years old, then it's almost closer to the mean value, right? What
Okay.
about if I pick the 6? The 6 is much also closer, so it means that it's almost the same. If I even pick 8, it's much closer, right? Now, if I go to the second example and I pick 7, and I ask myself, but the 7, that is the average. But somebody is almost 0 years old, which means that the person is just a day old or born and stuff like that. And somebody is around 14 years old. Then I ask myself, then if I randomly pick any of these people, you can see that it's not the same. There's a significant difference between 0 and 7. There's a significant difference between 14 and 7. So it might not be telling me the true story. So in these two examples, you might say that the first part, the mean, is a very good representation of the average than the second example. Now, given that you have understood this particular concept, then the issue of dispersion becomes much easier. Now, the question that we will now ask is, what is the differences? Now, you could see that the second example, you can see the distance between the deviation and then the scores are very wide apart. So this is the standard deviation. You can see that the values are very wide apart. But the first example, if you look at the distribution of it, we can say that the distance is much closer over here. So whatever predictions we are making is much closer to reality than it is in the second case, right? Now, given this, how well do the scores represent or shows in the distribution? The logic here is to determine how much spread is the scores and how much do the scores deviate from the mean. Now, if how much they are different from the mean, you're able to compute that, then it becomes easy for you to use that matrix to select which of the matrices best describe it, right? And that is just what the variance and the standard deviation is going to help us with. Now, we also think that the mean as the true score or as your best guess. If every S were very close to the mean, then the mean would have been very good predictor. But if they are not, if the distribution is not very sharply picked, then the mean is a good measure of the central tendency, right? So you can see the differences that we are trying to paint over here. That even though we can say that the mean is a measure of central tendency, in a case you can use it to make a case for a dispersion. If the values are much more closer to the mean or they are very picked around the mean, then you can see that you can even use the mean to even describe the issue much even better than if you would want to rely on the measures of dispersion, right? That is what we are trying to say here. So if you were to to use the mean to make predictions, you would be right or closely matched to the time, right? You would be very, very close to what the guess would have been. So if the scores are very widely distributed, then the mean is still your best. Remember, measure and your best predictor, but your predictive power would actually be very less. So in the case of the 254, you saw that even though the observations are very wide apart, yet the mean was still better for our description than the median, isn't it? But the danger over there is that the predictive power of our values will be very, very, very what less. We will not be able to predict exactly what would have been, because look at, from 10 being the next highest all the way to 1,000, and you have the median, the average value to be 254. You realize that if you are to make a prediction as to what the mean would have been, it would have been extremely difficult. You don't know whether to peg it at 200, you don't know how to peg it at 300, 400, or even 10 or 20 or stuff like that. Now, how do we describe this? The measures of variability, the mean deviation is very, very key. Mean deviation, the variance, and the standard deviation. Now, the first of the dispersion is the mean deviation. The mean deviation, this is also a key concept for describing normal distributions and for making predictions from them. Now, making these predictions, we call them the mean deviation or the deviation from the mean. How each observation are far apart the mean. Now, we would just calculate the average distance between what each observation. We must take the absolute value of the distance, otherwise they would just cancel out to 0. Now, how do we find the mean deviation? The mean deviation is saying that calculate your mean value, and you already know your mean value, isn't it, my brothers and sisters? We already know how to calculate the mean value. It's the summation of what? Of the observation divided by n, right? Now, what we are doing over here is that you first of all calculate that mean, and you pick away all or each of the what? Each of the observations from that mean, and you divide it by what? N. N is the number of what? Samples, or the number of observations in that data set. So once you do that and you sum the results, that becomes your mean deviation, which tells you that the average deviations of the mean on the average, how each observation are away from the mean value. Now, let's say we have this data set 6, 10, 5, 4, 9, 8. What would have been the mean? The mean, let's add them: 6 plus 10, 16 plus 5, 21 plus 4, 25 plus 9, 32. No, that's 34. 34 plus 8, that will be 42. If you divide this 42 by 6, which are the number of elements, right? 1, 2, 3, 4, 5, 6. You would have gotten an average value of what? 7, right? So the mean deviation, if you look at the formula once more, it is the mean minus what? Each of the observation divided by n. So in that case, you see that I now mentioned, of course, this one did not show quite clearly. Let me see if I can use my pen to be able to do that. So you can see that there is a bar at the top of this one, right? There's a bar at the top of that one. So now that we know this is how the formula is being constructed, then it becomes easier for us to know. So the 7, which is the mean, minus 6, the first value, 7 minus what? 10, 7 minus 5, the next one, 7 minus 4, 7 minus what? 9, and 7 minus 8. Remember, we are saying what? The mean deviation. So we will take the absolute value. Remember, in this case, it would have given us 1. The next one, it should have given us -3. But what are we doing? We are picking the absolute value. Please, I hope you get that. The absolute value. Then we go through all of those things. So you can see that the first step is telling us we calculate the mean value or the average, which is what we did over here. Then the second one is to compute the x minus s bar, x minus s bar minus x. I think they have been there. Let me check if I can rectify this quickly. Let me see. It's not really an issue, but let me see. It's because of the let me see if I can. Let me see if I can use the color codings to be able to do that. I think it's much clearer now, right? Yes. So you can see that the mean minus, and then you take the absolute value to get the absolute deviations, right? Now, once you get these absolute figures, you sum the absolute deviations. So that is just the deviation. You sum the absolute deviation. Then, after summing them, you divide the sum of this by the absolute deviation by the what? The n. So if you add this to this, you get what? Almost 22, right? That is 3 plus 1 and 1 plus 3, 4, 4 plus 2, 6, 6 plus 3, 9, 9 plus 2, 9
11.
plus 2, 11, 11 plus 1. That would be 12, right? Oh, I said 22 is 12. So now this 12, you now divide the 12 by what? The 12 will be divided by what? N.
6.
N is 6, right? So that would have given us around 2. So the absolute deviation would have given us what? 2. That would be the absolute deviation. So means that on the average, if you look at this observation, which is 7, look at the minimum value is what? 4, and then the maximum value is what? 10. And if you are saying that the 7 is the mean value, then it means that on the average, the difference between the scores you see over here, which are the 6, 10, 5, 4, 9, 8, from the mean is just 2 values each. So they are only on the average 2 marks scored different from this one. That is what it means. Now, on the average, each observation is just 2 units away from the mean value. That is a much different way of putting the same thing. That is what it means. Now, is it really what that easy? When we are calculating these mean value, it's not that always easy. The absolute values are difficult to manipulate algebraically, right? Because of the strict assumptions that if you subtract this from that, we are just maintaining the average value of it. That is what it means. And it might not look so straightforward as it is, because the absolute values would cause enormous problems for calculus. That is the discontinuity. We need something else for that. It is quite very difficult to manipulate, right? So in that case, we will rely on a different matrix, which is the variance and the standard deviation. Now, instead of taking the absolute values, we square the deviations of from the mean. This will yield us what we call the positive values, and this will result in the measure we call the variances. And then when we take the square root of it, we get the standard deviation. Take note of these things. Let me separate it much quite clearly so that it becomes easier for you. You see this thing? Let me drop it down. I'm taking my time to say this because oftentimes you see students say use them interchangeably. They are not the same. Probably I may want to have put it in a table to make it much easier. Okay. Just give me a second. Let me see if I just wanted to arrange it in a much better way for you to understand it. Okay. So this is what we are talking about. Hey, what has happened? Yes. So we have this here. I hope you have seen it. What I'm trying to do. So we have this also here. Yes. Yes. So this is what we are talking about here. So you can see that if you are doing this computation, these notations are very, very important. That anytime we are talking about the standard deviation, we use the small s for if it is a sample. But if it is a population, we use sigma. This is a small version of the sigma. Then when it is the variance, it is the square of the small s. If it is a sample estimate that we're talking about. But if it is for the population, you do the square of the sigma. Take note of this. I'm very, very keen on this because sometimes you may interchange them and it will cause some little changes in your computation. Please take note of it. We use small s for if it is a sample estimate that we are going to. So if it is a sample estimate that we want to compute and it is a standard deviation, we use small s. But if it is the variance of the sample, we use the s squared. But if it is the standard deviation of the population, we use sigma. But if it is the variance of the population, we use the sigma square. Now, this is the formula for each of them. So if it is a sample standard deviation, sample variances, you can see that the variance will always come with a square, right? So it means that you are doing what? Summation of Si minus S bar squared, all divided by 1 minus what? N minus 1. Now you see that the top part is the reverse of what we did at the mean deviation. The mean deviation, we did it what? S bar minus X. But this time around, we are doing S minus S bar. Don't worry about XI over here. SI over here is just telling us the individual's observation from which we are referring to. Each individual observation, right? So the S bar is the sample average, and then the S is the individual values in the sample, then the N is the count of the individual values in the sample. If it were to be the population, you see that you would have had this, right? Whereby if it is the standard deviation, it's just the square root of that. So you look at this, compare this to that. You look at this S over here and then the S square. The only thing that is the difference is that one is with the square root and the other is not a square root. So the simple answer or easier way to look at this sometimes is that whenever you are calculating the standard deviation or the variances of the sample, just calculate one and do take the square root of the other, which is, if you calculate the variance of the sample, you just take the square root of that variance and you get what? A standard deviation. If you have calculated the standard deviation already and you want to get the variance, you raise the power what? You square everything, then it would have cancelled off the square root of it. So that is one easier way to look at it. When it comes to population, also you see how the population is. Now you notice one unique thing about the population. You see that for the population one, you just divide it by only n, which is big N. You don't do -1 at the bottom part. Now you see the mean over here. The mean is the same as what? The S bar we have at the top here, or the S bar we have here. I think I told you that the first time we met that the mu is the mean of the population, whereas the S bar is the mean of a sample. I'll take it again. The mu, the one that look like U, is the mean value when you are dealing with a population statistics or a population figures, right? But if it is a sample mean that you are calculating, then you use the X bar. So these are the formulas that you'll be needing when computing the variance and the standard deviation of a sample and of a population. In the first case, you see that I did not bring the variance of the population. I expect you to know that, because the variance of the population is also just going to be only the things under the square root. So I'm trying to see if I can circle it. So this would have been the variance. Oops. So this would have been the variance. Have you seen that? This would have been the variance. That would have been the variance of, let me see if I can clean this one. Yeah. So what I have just circled is the variance of the, the variance of the population. Have you seen it? Which is almost the same as what we have at the top over here. So just to make things much clearer, you see that the variance of the sample is what we have here, the variance of a sample, and then the standard deviation of the sample is here. So you can see the only difference is that the standard deviation is with the square root, the variance is without the square roots. That is all. And you know that if I take the square of the standard deviation, I'll get the variance. If I square the standard deviation, I'll get the variance, isn't it? If I square it, I'll get the variance. Means that, remember, everything squared and everything square root, it means that that thing is raised to the power half, 1/2, right? So if I square it again, you can see that the half over there, what I'm trying to say is this. Let me try and then write it, even though it is going to be. So you see that S bar minus Xi all divided by n you see this, right? Squared. I'm just right. This is the standard the variance, right? But you see that this whole thing over here, from this thing here, from this thing down there, top here, this whole thing, it means that this whole thing raised to the power 1 divided by 2. That is the same thing. That is the same way of writing this. It means the same thing, right? It means the same thing. So some books or some formula sheet, if you see this, it means the same thing. Please do not say that that one you have not been taught, which can only translate into the top part over here will be remaining, and then the bottom part would have been just the n raised to the power half, or which is n squared. That's all. If you were to be doing it physical, we would have gone through the nitty-gritties of some of these things. So let's look at an example. Let's look at this data as 6, 10, 5, 4, 9, 8. We have looked at this value example before, right? The number of observations is what? 6. The mean value of this, let's calculate it. Now, let me see if I can arrange this in the box quite very well. Okay. Let me see. Okay. 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 So let's proceed rather than glossing over this. It will take our time so much. That will take so much of our time. But I think you can see it, right? You can see this. You see that what we are saying is that you have the first value here, the x. So the s, we can re-label the x, the x's. So you can see that 6 here, 10, 5, 4, 9, 8, right? Then the next thing that you do is that we says what? X minus S bar. Is that not the formula? S minus S bar. We are picking it from here. We are doing this, right? Trying to solve the variance and then the standard deviation. So X minus what? X bar. Or X minus S bar. Sorry. X minus S bar. Any of them, you could get the same thing, because at the end of the day, we will get the same thing. So this over here, we want to now bring every S. So it will now be 6 minus what? What will be the average value, which is the S bar? We have to compute that. To be able to compute that, let's look at this first. So you can see that the sigma S divided by N would have been 42 minus divided by 6, which is the 7. So it means that our average value is what? 7. So it would have been 6 minus 7, 6 minus 7 throughout, right? So let's go 6 minus 7, 6 minus 7, 10 minus 7, 5 minus 7, 4 minus 7, 9 minus 7, and then 8 minus 7. This would have given us -1, 3, -2, -3, 2, and 1. Then the next thing we do is to take the square of it. And once we take the square of it, we do the sum of it. You now sum it. So we sum it, and we had 28. Now we can now use this 28 to do our computation. Now the variance formula is what? Summation of what? X bar minus or S minus, because this one does not really change everything. That is why I was telling you that how you calculate the deviation does not really matter, because but what really matters is that you will square the deviation. So anytime you look at the differences between your mean values and the observations, it's called deviations. So once you square the deviation, whether it carries negative or positive, it becomes positive automatically. So that is why it does not matter why if you bring the bar first or the observations second, right? Now, if you have this, then the total number or the total score after taking the deviation square, which is given to us over here as 28, is divided by n. N is 6, and that would have given us what? The variance of what? 4.67. Then the standard deviation would have looked like this. Is the square root of the variance, because if you look at this, if you look at the formula we mentioned here, you see that the standard deviation is just the square root of the variance value. So once you have that, what prevents you from just taking the square root of the 4.67? Once you do that, please don't square this again, because this one is what we already have as what? 4.67. So once you take the square root of it, we get to a 2.16. But when we had this example, you realize that when we calculate the absolute mean deviation, we also had 2, right? The absolute mean deviation, if we went back to it, you see this. Absolute mean deviation, we had a score of what? 2, isn't it? And now we had the standard deviation of what? 2.16. You see that it's very, very close. So this is how we compute the standard deviation, the mean deviation, as well as the variance of the distribution. Any question? Maybe I'll have to get some few questions on this particular one and give you a series of example. But based on the previous one that we've done, I think I have left in those slides some examples for you to solve. I hope you've done that. This one also, I have to get some few questions on this and share with you. Are we on the same page? So that is how we can compute the standard deviation, variance, and then the mean deviations, right? Any question from here so that I can zoom into the next slide? Any question whilst I'm switching? I'm listening. Any question? And people always understand everything, no? And I hope that when the questions come, they will understand everything as such and then answer it as such.
Hello, sir.
I'm listening, please.
Sir, my concern has to do with the formulas that you gave. If I remember well, you said the formula that ends that has the denominator small n minus 1. That one is usually used for sample. Those ones are used for samples and not the
Yeah,
population.
when you are doing sample estimation, when you are doing the sample
Yeah,
estimate for the deviation, the mean, how do you call it, the standard deviation or the variances.
The variance. But what we use right now, the data, is it on a sample or is on a population? Because I realized that you were using the capital N instead of the small n minus 1.
Exactly. That's the right question you ask. Which one are we giving? So in this case, we are just assuming that this is a population figures that we have. That is
Okay,
just the
thank you.
assumption. Now,
Thank you very
the
much.
next thing that I was expecting you to say is that okay, then why, if we use the capital ones, then why are we now using the letter small s to
Small
represent it? Because the small s would have correspond to what, a sample estimate, which should have come with small n minus 1, isn't it? So over
Yes.
here, the concept is what we're demonstrating, that, hey, if it is for a population, just go ahead and use the sigma symbol and then use the capital N. But if it is a sample, use the word small s and then go ahead and use n, small n minus 1. That is what we are trying to preach over here. All right. Let me try and then project this next thing for us to do quickly. It looks like today we are not much fast enough. Okay, can you see my screen now?
No, sir.
No, dog, we can't see
Okay.
it.
Okay. Let me see if I can share this one with you. Yeah. I think we can show now. I hope you can see it now,
Yes, sir.
right?
Yes, sir.
Okay.
So,
So we want to start with some basic other descriptive statistics, where is probability distribution, a topic that a lot of you are always afraid of. You go through very, very short. So anytime you hear about probability, we are talking about what? Chances, right? We are talking about things that have a possibility, right? Things that has the likelihood, things that has to do with chances, things that have to do, it may happen or it may not happen. So the moment you hear probability, it is likened to any of these terms that I have used, right? You go through the meaning of it. What are some of the basic rules of probability? Then we look at a Bayesian theory and then the principles of counting. Our brothers and sisters that have been doing lottery, you hear this word from them a lot, permutation, permit for me, that thing. Today we will also learn about permutation and stuff like that. Then look at some practical questions. Now, what then is an experiment? Experiment is just an act or a process of observations that would always lead to a single or many outcomes that cannot be predicted with certainty. So there is nothing. In fact, if there is something that is an experiment, no one can ever predict the outcome of that experiment with 100% certainty. We therefore suggest that the moment you are experimenting something, you are having at the back of your mind that that thing can result in that or it may not result in that. It can get to you the ultimate decision or it may not get to the ultimate decision. That is what it means. Now, it is an activity with a set of what we call an unknown observable resource. These unknown observable results, we call them outcomes. So a typical example is when I decide to uh, toss a coin in the air. In fact, it is an experiment I'm conducting because the possibility that I'll observe the tail or I'll observe the head of it, I do not know, right? Because those observations, I do not know what the results would have been. That result that we will observe at the end of tossing that coin into the air is the outcome. The results would be an outcome. So this outcome can either be a head or it can be a tail. It goes also on with a fair die that is being tossed. The outcome could be 1, 2, 3, 4, or up to 6, isn't it? I use the word a fair die in the sense that you see sometimes those days when you are playing Ludo game, you have used the cube for a very long time, so it becomes so small and round, such that sometimes if you are not lucky, you throw it and it will go and land on a certain edge. You don't know which number appears. That is not a fair die. That is not a fair die. That is why I use the word fair die. The fair die will mean that each of these 6 surfaces have the equal chance of being observed. Now, an experiment have more than one outcome. If an experiment has only one outcome, then it is not an experiment. Take note of that. Or should I even call it an experiment? Because we said that experiment will always have 2 or more outcomes. So if an event, an act, or a process has only one outcome, we cannot call it an experiment. We cannot call it an experiment. So a typical example is that if you toss a coin once, that coin might result in 2 outcomes. So far as the outcome is going to be more than 1, then we can say that it's an experiment. Also, observation is just the possible results of the experiment, the actual results of that experiment that you conduct. Each outcome has to be what we call mutually exclusive from the other. When we say mutual exclusivity, what do we understand? We say that when we toss a coin, for example, and we expect either a head or a tail, we are saying that the occurrence of one should mean that the absence of the other. The occurrence of the other should mean the absence of this one, which means that when we observe a tail, there shouldn't be any possibility for us to observe the head. If we decide not to throw it again, we must not see the head if we don't decide to throw it again. So in that single experiment that I tossed the coin, I should be able to see one and only one outcome, not 2 outcomes. If there are 2 outcomes, then it is not a good outcome, right? Now, for example, numbers between 6 and 10, anytime we are selecting some individual randomly, for example, from a class or something, a queue or somewhere, there could be an outcome, right? Now, a sample space is also a set of all possible outcome of an experiment. Now, you see that coin that I'm going to toss, how many possibilities do I have? I have 2 possibilities, right? I can experience a head or I can experience a tail. These 2, things that I can experience, we call it what? A sample space. These are all the possible number of outcomes that I can experience when I toss a coin once, right? The next one is example is that if I toss a quip, a die once, my sample space would have been all the possible outcome of tossing that coin, right? So all the possible ones will be from 1, 2, 3, 4, 5, and 6. These are my sample space, right? So take note of these example, this terminology. Now, event is an act. It is a set of outcomes of an experiment. So typically, we are saying that a subset of a sample space is what we call an event. So some portion of that is an event to which the probability is actually assigned. So which part of this sample space that we are assigning the chance that it might occur or it might not occur, that portion of the outcome or the possible outcomes that we are assigning a certain set of probability to it is what we are calling an event. So let's say, for example, you toss or you roll a die on a Ludo game, and you are expecting 2, 3, or 2 or 3 to appear. Those 2 or 3, if you are assigning probability to them, then that becomes the event, because these two things have a certain possibility of appearing when we roll that die or not. So once we are able to assign that probability, or we should be able to assign that probability to that aspect of the sample space, then we are talking about event. Mutual exclusivity, or what we call the disjoint event. Two or more events are set to be disjoint or mutually exclusive if the two cannot occur at the same time. A typical example is a rainfall pattern or so, or weather pattern. Let's say, for example, every given day when you wake up, there is only two possibilities. Either it will rain or it will not rain. Is that not it? Can you see in the day that it will rain and it will not rain before? If that day it rain, means that it will not rain is totally off the table, right? But the day that it will also not rain and it will rain means that it will not rain will not occur at all. Again, if it does not rain, means that it will rain has also been ruled out all of a sudden. When we come to the coin issue, you notice that anytime you toss a coin and the head appears, means that the tail will not appear again. In that case, they are mutually exclusive. Two events cannot happen at the same time. Now, jointly or collectively exhaustive events. If the events are exhaustive, means that we are saying that an event is exhaustive or joint if at least one of the events must occur. So let's say, for example, it is exhaustive, means that if I'm tossing a coin, what I'm trying to say is that under no circumstances should I toss the coin and I'll say that, oh, I did not see a tail and I did not also see a head. It can't happen. Collectively, I must see an option that happened, and that we are saying that it must be collectively what exhaustive. Now, an event is exhaustive or joint if at least one of the events must occur. Let's say, for example, from a 6-sided die, right? The events 1, 2, 3, 4, 5, and 6 are mutually what? Exclusive if after the experiment one of these elements is observed at the end of the day, right? That way, they might be what? Very exclusive and at the same time exhaustive. Now, we often use sometimes this John Vin diagram to be able to depict some of these set operations and things like that. It's a very, very powerful tool that we use to learn basic probabilities, right? To be able to look at intersections, union, and then ODs, right? You look at a bit of it. Now, anytime you see this notation, it means it denotes a member of something. So if we say that Z is a member of M, it read as Z is a member of M. So the Z, that symbol M, means that Z is a member of M. When we use the O/, or which is called the file, it simply means an empty set. It means that the set that contains nothing, it contains zero, element or no element. That set is called a null set, right? It contains no element and it is a subset of every set. In fact, that is the very uniqueness of a null set. A null set is part of every set that you talk about. Then we have U. U denotes union, right? So if I say EUF means that E union F, E union F, right? E union F. Now, E union F is a set of all the E's or F or both of them. So if I say E union F, another practical way of stating it is that I'm saying that if I have two classes, for example, one class I call it class E, and I have another class F, and I say that what class E union class F. What I'm trying to say is that all the elements of E plus all the elements of F, all the elements of E plus all the elements of F, plus if there are some individuals in this class that belongs to each of these two classes, means that they are the both parts, right? They are the both part. So when we have that, then we can always refer to them as the union of these two classes. So a typical example is that, let's say that we have a sample space to be what? A, B, C. And we have, let's say, class B is what? B and C, and class F is A and C. So if I say A union F, which means that I will list all the elements in E and all the elements of Y, all the elements of F, all the elements of E and all the elements of what Y, F, to be able to get the union of it. If I list all of them, you could see that C is still common to both of them, but you only list it as one, right? You list it as only one. And that C becomes what we call the next thing that we will talk about, intersection. Intersection is just the one that will be common to both of them, right? So it reads as what? E intersection F is the set of all elements of both sets or both set E and set F. So the values or the elements that are common to each of these sets is what we are calling the intersection. So in that previous example, you could see that C is the intersection of E and then F, right? So E intersection F is C in this case. So we give also an example here. Then we also talk about the disjoint set or the mutually exclusive. They are different. They don't intersect. So once the intersection, will talk about the one that is common here and the one that is common there. The disjoint or mutually exclusive one will be those that are not in them. So a typical example is that E and F are mutually exclusive if and only if there is a null set for each of these two. Now, when we roll a die, for example, event 1 outcome is below 3, right? If it is below 3, so we have 1 and 2. And event 2 is having some values above 4, so we have 5 and 6. So the E intersection N will be what? Will be 0, which is just the null set, right? Which will be 0. So you don't write 0 as it's supposed to be because it's a set. If it is 0, you use the word the file. That's the only difference between mathematics, main mathematics, and then this probability stuff. You can't say just 0. You have to use the far. So these are some of the denotations and how we can be able to look at the mutual exclusivity and then intersections and stuff like that. You see that A is the circle of A is not close to the circle of B, right? So it means that they are disjoint. So the intersection over there is 0. There's no intersection. They did not intersect at any given point. So it is actually 0. So in that case, you will see that the A union B is going to be 0, which is just the far. Then if two sets are mutually exclusive, then they have no outcome in common. That is what it also means, that they have nothing in common. They can't occur at the same time. The outcome of the random experiment cannot belong to both A and B, right? It cannot be both A and B. Then we also have X/Y is the set of elements in X but not in Y. So anytime you write X/Y, we are saying that all the elements of X that are not in Y. So we are talking about the onlys over here, right? Those that are specific or exclusive to only one of the sets. So to be able to write that, you say that what that value, that set slash the other set. So we are talking about only the split members of X. Then we also have the symmetric difference of between the X and Y, whereby we say that the X delta Y is just the symmetric difference of X and Y. It's just the set of elements in either X or either Y, but not both. So it means that we are looking at the separated aspect. If the two circles have met, we would have looked at other aspects that have not merged or have not crossed each other. So we are looking at the onlys. So these are some of the things that then we also talk about complement of a set. If you are writing a complement of a set, the set raised to the power C, then it means we are saying complement. Now, what then is the complement of a set? We are saying that outcome that is not in E, but in the sample space. So if you have a sample space to be 1, 2, 3, 4, 5, 6 for a die, a die that you rule. Sorry for that. I think a die that we will throw. Then we are saying that the outcome is not in E, but is in the sample space. So a typical example is that if I now pick an outcome to be what 0, or even if I pick an outcome to be 7, you can see that when you are throwing a die, you cannot see 0 and you cannot as well see what 7. So that becomes a complement. It's just adding up to the element of that set. So the set A is a member of S, but not a member of A. So in that case, let A be any event that then if let's say A is any event, then the complement of A would be denoted by what? A raised to the power slash or A slash at the top, defined by A does not belongs to. So he's just trying to say that A does not belongs to that group of individual. So the A bar occur if the event A does not occur. So it means that it can even happen without the other one happening. They are the cumulative law of a set, right? If I say E intersection F is the same as F intersection E. If I say E union F is the same as F union E. If I say E delta F is the same as F delta E. These are the cumulative law of identity of a set. But for the associative rule, right? The associative rule. If I say E union into bracket F union Z, is the same as if I say that E union F union Z. Same as when you use the intersection, right? Same as when you use the intersection. Then we have also the distributive rule, where we says that it's just like E intersection F union Z. If you do that, it's just telling you that if you multiply the E by what is in the bracket, if it were to be algebraic, we would have done it like that, right? So that is what is being displayed over here. So you are just trying to say that E intersection F, then you bring union. Union would definitely pick the value of and or plus in statistics, right? In statistics. Then you would have had the E intersection F union E intersection what? Z. Similarly, when you have the union E union into bracket F intersection Z, so it will mean that the E union F intersection E union Z. That is what it. Then the De Morgan law, which also talk about the F raised to the power. So we have the E intersection F, would definitely mean that F raised to the power, C union E is raised to the power C. So it's just trying to say that just like the union would means that the complement of each of them would have been the intersection for E union F. You get to know more about the De Morgan as we move on. Now, in problem, you will recognize that you are working with what we call the union, intersections, and complement more. If you are talking about union, it is normally the word that will be used to describe the set are or. You'll be using the word or to be able to describe. If you're interested in intersection, you'll be using the word and. And when we are using the word complement, we'll be talking about using not. Take note of all this. It's going to be very, very important to keep these things so that we can use them when because you only be giving a statement and you know that the or would mean union, the and will mean intersection, and the not will mean complement. What is the order of operation for all calculations within parentheses? Parentheses are done first, right? All things whenever it's just like any algebra. All calculations that are in bracket are done first before squaring or raising to other exponents is done. Multiplying and dividing are done third and should be completed in order for the left to right. In order from left to right. Then summations with the summation notation is also next. Then the last one is that any additional additions and subtractions is done last and should be completed in order from left to right. Now, whatever thing we're talking about over here is the fact that how do we use the board mass? This is basically about what board mass stuff, right? Board mass stuff. So, my brothers and sisters, where we have gotten to is another critical aspect of starting the actual probability stuff, but we have looked at the set, and then how to do the union, and then the intersection, the complement of a set. I'll pause over here, invite questions, and then on Wednesday, I will meet you, and then we will pick it, or we'll take it from there, right? But before then, I'll try and then see if I can get you some more examples of some of the things, if possible, with some solutions. For the solution aspect, I'm not guaranteeing that. So I'm listening. Any question? Any question?
Okay, thank you, Doc. I think you've explained most of the terms, but maybe I guess when we meet on Wednesday, we'll be able to get the.
Okay. All right. All right. Then I will leave you guys here, and then I'll meet you on Wednesday, right? Okay. All the
Same
best.
to you.
Take care.
Thank you.
All right.
Same to you, sir.
Okay.
Thank you.
It seems Doc has left also.
I didn't meet you guys. Gabi here. Hello. Yes. Good morning. I'm Adam here and I was there.
Let's go.
From Babo here. I'm girls who see what they serious.